Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Welcome back to the deep dive. Today we're tackling something that's one of the biggest and maybe least discussed challenges in biomanufacturing. Scaling up microbial fermentation.
Yeah, it's a huge topic.
We're talking about everything from biopharmaceutics to large-scale enzymes. And if you've ever been in development, you know the models you use. They all assume this perfect theoretical execution.
Ideal conditions, stable infrastructure.
Exactly. But then you move from that clean, small-scale lab to a massive industrial reactor, and the reality hits you. You're not just managing biology anymore. You're managing this sprawling, messy, socio-technical system.
That's the perfect way to put it. And our mission today is really to dig into the sources and find those implicit process variables. Because the second you move from the bench to manufacturing, your success is no longer just about the biology. It becomes completely tied to the people, to the organizational discipline, and the physical resilience of the building itself.
Yeah.
We have to start framing these things, these latent risks, not as random disturbances that just mess up a batch now and then,
but as actual inputs.
as measurable inputs. They directly shape how durable your campaign is, your sterility, your reproducibility. They're process variables, plain and simple.
Okay, let's unpack that. And if that's the premise, I think the place to start has to be with the people actually running the equipment, right? The operators.
Absolutely.
We spend so much engineering effort on, say, preventing a pump failure, but operator behavior is often just treated as some annoying risk we need to train away.
And that's the fundamental mistake.
Yes.
Operator actions are not external disturbances. They're recurrent inputs. I mean, their technique can shift everything from sterility assurance to the oxygen transfer in the tank.
And the sources say these deviations, they're not random, they're clustered.
They're episodic and clustered. Think about it. A rushed shift change, a high-stress maintenance job. That's where things happen. And that clustering makes them totally invisible to standard process control charts.
So we need to look at the specific places where human variability is most likely to introduce risk. What are those error-likely tasks in a big microbial fermentation suite?
Well, they tend to cluster around these high-leverage control points, especially anywhere that you compromise the sterile boundary. The sources really zeroed in on 4 major vulnerabilities.
Okay.
First, and most obvious, is sterile boundary crossings. This is your sampling, your inoculation, connecting feed lines. These happen all the time. And even a tiny variation in aseptic technique, maybe because someone's distracted, can seed contamination and ruin weeks of work.
Every single time you open that system, you're rolling the dice.
You're rolling the dice, exactly. The second area is just catastrophic. CIPSC configuration errors.
Right.
An operator might line up the wrong valve or leave a drain blocked.
Oh, that's a nightmare.
It is.
Yeah.
Because the system, the automation recipe runs. It says it's complete. But if it's misconfigured, you can have cold spots that completely undermine the whole sterilization. The system says green, but the vessel is compromised.
And that's so insidious because you don't find out until, what, day 4, day 5 of a 10-day run when things start to look weird?
Or worse, when you see contamination. The third one I call the silent killer of productivity. Foam and antifoam interventions. You need antifoam. But if you over-add it to knock down some foam, you can just crush your oxygen transfer coefficient, your PFA. The antifoam literally coats the bubble surfaces.
So you're choking the culture.
You're choking it, gets forced into oxygen limitation, starts making byproducts, your yield tanks. And all the while, the dissolved oxygen sensor looks perfectly fine because oxygen isn't being consumed fast enough.
That's a fantastic example of how fixing one visible problem foam creates a hidden, way more expensive problem.
And the last one is just manual data entry and undocumented adjustments. A team can spend a week blaming a batch failure on the strain or a bad sensor because nobody logged that one time an operator manually bumped the agitation speed up. That ambiguity just destroys your root cause analysis.
So if we accept these errors are predictable, then the engineering systems have to be designed to absorb them. You can't just demand perfect compliance forever. Retraining alone is not the answer.
That is the core philosophy. You have to design for failure. Going back to that microbial example, say a fed batch run suddenly starts making ethanol. The first assumption is always biological.
A mutation or something with the media.
Right. But if you dig into the batch record, you might find a little unlogged note about an antifoam addition on the graveyard shift 2 days earlier. That one action, totally invisible to the control system, dropped the kTha and forced the culture into oxygen limitation. The human factor root cause gets misdiagnosed as a biological problem.
Okay, so if the system needs to absorb error, that means the people need to understand the consequences of their actions. Which brings us to training. This has to be about more than just following steps. It's about intent-based competency.
Precisely. You need operators who don't just follow recipes, they understand why. Why are these the critical parameters? What do the early signs of failure look like? Procedural training makes operators who can run the equipment. Intent-based training makes operators who can save a campaign.
So what does that competency model actually look like? What does it require beyond just reading an SOP?
It needs 3 critical literacies. First is mechanistic literacy, understanding the physical and biological connections. They need to know the direct links between, say, oxygen uptake rate, mixing limits, and overflow metabolism. They have to get the physics of how antifoam impacts mass transfer, not just foam is bad.
Okay, that makes sense. And the second one?
Sterile boundary literacy. They have to know instinctively what's inside the disciboundary and what's outside, and why taking a shortcut, even for a second, could compromise a multi-million-dollar campaign. It's not just a procedure, it's the single most important barrier to failure.
And the third literacy feels more important than ever, with digital records and audit trails.
Data literacy. It's understanding LCOA+. That data has to be attributable, legible, contemporaneous, original, accurate, and the plus is traceable and available. This isn't just good handwriting. In biopharma, every single data point has to be verifiable.
And this is where understanding the intent really pays off. Let's walk through that training scenario you mentioned.
Okay, so an operator is running a substrate-limited feed. The whole point, the intent, is to keep glucose low to avoid making byproducts. Now, if they see a temporary dip in the glucose reading, the procedurally trained operator might just crank up the feed pump to hit the number on the screen.
Correcting the deviation.
Right. But the intent-trained operator knows that a big pump increase will probably overshoot and trigger the exact byproduct formation they're trying to avoid. They understand the biological goal is more important than the immediate number.
So they hold the line or that they make a smaller adjustment.
Exactly. And the decision-making is the difference between a high-yield, reproducible campaign and one that's all over the place.
Which brings us to the facility itself, because even the best operators can't fix equipment that's slowly falling apart. You talked about facility resilience sustaining performance over entire campaigns, not just single runs.
And the biggest threat to that is campaign drift. It's not a sudden failure, it's this slow, creeping degradation, seals aging, heat exchangers fouling, filters loading up. The result isn't a single batch failure, but a gradual, creeping increase in variability over time. You get pushed closer and closer to your process limits.
So we have to treat this drift as something we can measure. What are the key indicators we should be trending, these implicit variables?
The sources point to 4 really practical ones. First, your SIP heat-up time trend. If it's slowly taking longer to get to sterilization, panic campaign after campaign, that's a sign. Insulation is degrading or you have scale in the jacket.
Okay.
Second, the gas filter tilt-to-P trend. The differential pressure. If that's rising, your filter's getting clogged, which stresses your whole aeration system. Third is cooling performance. If you see the cooling valve having to open more and more over time to maintain the same temperature, that's your heat exchanger fouling. You're losing capacity.
And that's a tricky one because if you're still hitting your targets, it's hard to get management to invest in fixing a slow trend.
That's the challenge. You have to quantify the risk.
Yeah.
You're losing your safety margin, you wait until a heat wave hits, and suddenly you can't control temperature at all, and you lose the batch catastrophically.
And the last one is about cleanliness.
Yes, the cleaning burden trend. Are your CIP cycles getting longer? Are you using more chemicals? Failing rinse conductivity. That means you've got residue building up, which is a direct precursor to biofilm and contamination risk.
And this campaign drift gets amplified by organizational issues, right?
Yeah.
Especially in 247 operations. The sources call out incomplete shift handovers as a huge failure point.
A massive one. Incomplete handovers create what they call state uncertainty, and they allow small problems to just become normal. You need structured handover protocols. What's the sterile boundary status? What alarms are active? What's coming up?
And clear triggers for when to investigate something.
Yes. You need to prevent the normalization of deviance. That repeated little DO oscillation isn't just how the fermenter runs. It's an early warning sign. And none of it works without data integrity, without LLCOA, plus MIO. If you can't reconstruct what happened, you can't solve the problem.
So this all points to needing practical, engineered solutions. Let's talk about poka-yoke, mistake-proofing.
Poka-yoke is where this philosophy becomes reality. You design the system so the wrong action is hard or impossible to perform. For sterile boundaries, this means things like keyed or gendered sterile connectors. You physically cannot plug the inoculum line into the acid feed port.
Just that one change must save millions.
It does. It doesn't just save the product, it saves the cost of the massive contamination investigation that follows. We also use interlock valve lineups in the PLC. The transfer valve simply will not open unless the system confirms the right SIP sequence has been completed upstream and downstream.
What about feeding errors? Those are so critical in these high-density processes.
Gravimetric feed control with plausibility limits. The system watches the weight of the feed container. If the pump is running, but the weight isn't dropping as expected, it alarms. We also use barcode or QR verification for solutions. The operator has to scan the right bottle before the pump will even turn on. No more adding 10x concentrated glucose by mistake.
You can even use mistake proofing in the control room itself.
Absolutely. Mandatory units and range checks in the SCADA system. If an operator tries to type in a pH of 25, the system should just reject it. It prevents simple typos from becoming catastrophic failures.
What's really fascinating here is that we can use these tools to monitor human factors proactively. We don't have to wait for a contamination.
We can, and we should. You can track the intervention count per batch. The more times that sterile boundary is manually crossed, the higher the risk statistically. You can look at alarm and override behavior. How much time are operators spending in manual mode? You can also track the near-miss reporting rate. Hearing about what almost went wrong is often more valuable than analyzing what did go wrong.
Can you give us a real-world example of this in action?
Sure. Think about producing recombinant E. coli for insulin. It's an incredibly sensitive process. Before these kinds of controls were common, they might have a significant deviation traced to human error every 20 batches or so. After they implemented just two key things, keyed sterile connectors and interlocked valve permissives, they saw a sustained 20 to 30% reduction in those deviations. It's proof that engineering the human factor out of the equation directly and quantifiably reduces risk.
Let's pull this all together now into the bigger quality framework. How does all this fit with the regulatory picture?
The key is to see the regulatory mindset not as paperwork you do at the end, but as scientific discipline you apply right from the start. That's the heart of quality by design, or QBD.
So QBD means defining a process that's robust enough to handle the real world.
Exactly. It tolerates realistic variation shift changes, utility drifts, while still guaranteeing product quality. And your risk assessment has to explicitly include human factors and organizational weaknesses right alongside things like pump failures.
And the control strategy that comes out of that.
It has to be layered. You use engineering controls first, the interlocks, the keyed connectors, then you use procedural controls, the SOPs, second. Training is reinforcement. It should never, ever be your only barrier to failure. When you do that, your pilot data becomes credible evidence for your manufacturing strategy.
This has been a really powerful deep dive to try and synthesize all this. Where does this leave us on what makes a fermentation campaign successful?
It leaves us with the understanding that human factors, facility resilience, and organizational discipline. These things define the boundary between a process that works in theory and one that works reliably in a factory. These latent variables, the quality of a shift handover, the age of a seal, can completely overshadow the biological variability, especially in long campaigns running at the edge of the equipment's capability.
So campaign durability isn't just about having the best biological strain. It's about meticulously trending those slow drift indicators and operating in a way that preserves your long-term reliability.
And to leave you with a final thought to mull over. If we accept that contamination risk is proportional to the cumulative number of manual boundary crossings in a batch, how could your facility redesign a complex process? How could you use something like a closed, single-use manifold with keyed connectors to turn a high-risk, multi-step manual process into a single low-risk engineered solution? And by doing that, quantitatively build human factor variability right into your process design space.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Ernala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.